Okay, this video will briefly cover what does generalization, overfitting, and underfitting mean. Generalization, starting here, is essentially what is your model's ability. If you build a machine learning model, what is that model's ability to accurately predict or classify future information or unseen information? Okay? If I build a model based off of 100 data points that I have, or 10,000 data points, or 40 million data points, the next time I want to see what my model thinks about a data point it has not seen before, or I want to look at what could the future data points look like, you want your model to have a fair ability to generalize to new data, whether it's unseen data or future data, depending on what kind of supervised learning that you might be interested in. Okay? And under that topic of generalization, you have these concepts of overfitting and underfitting. Okay? And I did these little doodle graphics down here to help me memorize what I was going to say right here. And so the first one, we'll start this one over. So we're going to talk about overfitting and underfitting. Let's say you have data points that look just like this on a graph. And I have an X just to represent different data points on this graph. The x-axis can be anything you want. The y-axis can also be anything you want. You don't really need anything specific to know what's going on here. Okay? But these x's are the data points that are in my data set. Okay? And now I'm going to draw a line that represents what my model predicts. So imagine these little ticks down here are just simply the x-axis values for those. And how about this? I'll even write in the numbers just so it looks more like a traditional graph here. 6, 7. Okay? And the model, again, is going to be this straight line. I'm going to just draw it connecting these x's just like that. Okay? This line runs through every single data point. This is what we call overfitting. The model is correctly predicting the data that I already have, but the moment I introduce new data for my model to predict, let's say there's a data point that's over here. Okay? The model, let's say this x is at 7. The model thinks 7, the y value, is all the way up here, which is way too far away from that x. Okay? That's what we call overfitting, when the model is fitting so well to the training data that it doesn't even matter where the new data point is, it won't even think about it. Okay? So we need a model that doesn't fit so well to this. It's interesting that it does, but we need something that is a little bit looser so that this x over here is close-ish, if not on top of this model line that I have here. Okay? So let's do some erasing now. See how well I can do this. Very good. Okay, so we're back to how we started. The x's are just our data points. So let's now talk about underfitting the model. Well, if overfitting means that we just ran through all the points, underfitting must mean that we don't really run through them much at all. Let's say I just take a straight line and go all the way out. Okay? And immediately you could see here that this line that I just drew doesn't really have much to do at all with the x values, in the data points in the data set, rather. Right? Let's say I wanted to, hopefully I don't regret this, let's say I just erase all my data points and let's say they were over here. I underfitted the model, but I have the same line. The data points changed entirely. Okay? So the thing that you want to understand here is that this model that I just drew here didn't really learn from the data points. Right? It just saw, okay, there's like a kind of an upward trend, so I'm just going to go in that direction. Right? That's what underfitting is. Okay? I'm going to introduce a new data point. Let's say it's somewhere out here. This might be at an x value of 9, for example. Okay? Now, I want my model to avoid underfitting and avoid overfitting. Okay? So, what I'll do is that I'll begin to draw my model. It'll see a data point at 2. It says, oh, this is a little bit high. Let me go just a bit up a bit. Right? And it continues that direction. Oh, at 4, there's one over a little bit lower. We'll go down some, continuing to the right. Oh, there's a data point up here. We should go up a little bit, but not too far, because it's right at 8. There's a data point way down here. So then it just continues on. Oh, look, we actually passed right through our brand new data point. Okay? The model didn't overfit because it's not matching exactly to where the data points are. And it didn't underfit. Let's see if I get rid of these dashes here. It didn't underfit because there is a little bit of complexity that you can see in this model. It changes directions and it swivels and swerves some. And we find a sweet spot in the middle such that when we have new data introduced, our model can get actually pretty close, if not right on top, of where that new data point is. So that will explain the ideas behind overfitting and underfitting. And I will erase that now so I can continue on. So I also have a little graphic down here. This is accuracy versus complexity of the model. And this ties right back in with generalization, overfitting, and underfitting. So what's going on here is that these x values on the x-axis represent the model's complexity. And the y values here represents the model's accuracy. This graph will look something like this most of the time. At least as an introduction to machine learning, you might see models that look like this. As you get to more advanced levels of machine learning, which I am not at yet, then you may begin to see a different shaped curve as opposed to this one I just drew here. Right? And again, let's zoom in here. And actually, let's draw it a little bit bigger so it's easier to see. Right? This is our bell curve. The x-axis is model complexity. And the y-axis is accuracy of our model. In this region, in the lower left, is where we see underfitting. And on this portion is where we see overfitting. The more complex our model is, the more likely it is to overfit. And conversely, on the other side, the less complex model is, the more likely it is to underfit. And I'll leave you with one last illustration of mine, hopefully they're not terrible, to underline what this graph is saying. Okay? So, let's imagine if you've taken any kind of algebra or calculus class, you might see a function that can be represented with a line that looks something like this. Okay? Now, you know that a bell curve, let's say the graph of x squared, is going to look something like this, right? And you know the graph of x cubed is going to look something like this, right? And you will see the more that you increase the polynomial coefficient, or the exponent, I should say, of a model, you can get even more squiggly lines, right? And that's kind of what we're seeing over here. We see 1 hump, 2, 3, 4 humps, and it just continues on going out, right? We could say that this graph, if we drew the entire thing, might be x squared or x cubed, x to the fourth, x to the fifth, x to the sixth. And the higher this number is right here, the more squiggly lines we see. Okay? That represents model complexity. Because let's say our function, which represented this model, was x to the sixth plus x to the fifth plus x to the fourth plus x to the third plus x squared plus x. These are a lot of different numbers inside our model, right? The x can change by just a small amount, but then this function, the result of it, will be a huge number or a huge different number compared to what it was previously, right? If x is 1, then this is equal to 6. If x is 2, now this number is crazy huge, right? That's model complexity. But if we just erased x to the 6th, the 5th, the 4th, to the 3rd, and just made it x squared plus x, then if x is 1, then this evaluates to 2. If x is 2, then this evaluates to 6, right? Which is a much smaller change between values of x, right? And a model like that, if we get rid of this here, may look something more like this, right? The model is much less complex. It's much more understandable. It's much more predictable. That's how you can understand model complexity. Okay, so just remember, you want your models to be able to generalize to new information. You don't want them to overfit. You don't want them to underfit. There is a sweet spot, generally in the middle-ish area, that your model will perform best, meaning that its accuracy will be at its highest.